Hi, this is Mr. Pinter. Welcome to part 2 of our video on chapter 2. In part 1 of this video lecture, we looked at the impulse response and convolution for discrete time systems. In this part of the video, part 2, we're going to basically do the same thing, impulse response and convolution, but this time we're going to do it for continuous time systems. So let's look at an introduction to the impulse response for continuous time systems. We saw in the last part 1, that the simplest input signal to any system is a single unit impulse. So for continuous time systems, remember our impulse is a function which we designate as a delta function, delta of t, and it looks like a spike. And remember, this spike is infinitely tall and infinitesimally narrow, but it has a total area of 1. If we put this impulse into our system, then the system is going to respond and produce what's called the impulse response, h of t. So we're, again, using delta for our input and h for our output. The difference now, of course, is this is continuous time. So our impulse response is going to be some continuous function of time as shown here. This is just an example of what the impulse response might look like. So the importance of the unit impulse response, h of t, is that for LTI systems, we can use superposition to construct the output y of t for any input x of t just by scaling and shifting h of t. Thus, the unit impulse response completely characterizes the system. So this is, the same thing we saw in the last lecture on discrete time. We can figure out everything we want to know about this system just by knowing its impulse response. So the impulse response is a very important way to characterize a system. So before we get into convolution for continuous time, let's do a little bit of groundwork here so that we can derive the result. So this is a review of the continuous time sampling or sifting property that we actually introduced back in chapter 1. The sampling or sifting property basically says that you can think of a function here, x of t, or a signal x of t, as a sampled version of x of tau here, using an impulse to sample the function. Okay, so the other interpretation of this result up here is that we can think of x of t, our signal here. Imagine, of course it's a continuous signal, all right, but imagine breaking it up into an infinite number of little values here, all placed right next to each other. Okay, so we're sort of looking at a discrete version of x of t. And we can think of, at least hypothetically, as taking our continuous smooth signal here and separating it into its values at each value of time. And of course there would be an infinite number of these. Okay, so that's kind of what this integral up here is telling us. It's saying that x of t is the sum, remember an integral is just a sum, of all of these products of the value of the sequence at tau multiplied by a delta function there and then integrated. Okay, so this is sort of a, an abstract way to think about a continuous time sequence, or I'm sorry, signal like this, and it's going to be useful for us in order to derive the convolution property, which we'll get to next. So here is one way to derive the convolution property for continuous time systems. So let's start with our impulse response again. So over here on the left, we have our delta function. This is the impulse, and the system produces h of t, which is the impulse response. And let's just assume that it looks something like this curve right here. So if we shift delta t over by an amount of tau seconds, then we have delta of t minus tau going in. Well, then we know by time invariance, our output is just shifted by the same amount. So this function here, h of t, just gets shifted over by an amount given by tau. So now it appears over here. It's delayed. We can also scale the input. If we take this shifted delta function, delta of t minus tau, and scale it by the value of a function at time tau, we have x of tau times delta of t minus tau, and all that does to the output is, because of linearity, it just scales the output by the same value of x of tau. So if this was h of t minus tau up here, then x of tau times h of t minus tau is just going to be a taller version of this. Let's for example say that x at tau seconds is equal to 2. Well, then this thing right here is just going to be twice as tall here. So this is just basic scaling. So we're doing shifting and scaling here. So by scaling, we can do another trick here, which is going to help us with the calculus that comes up. Let's multiply the input by some amount delta, this is an uppercase delta, some time interval, delta tau. Again, by scaling, all that means is over here, we multiply by that same amount on the output. And then we can use superposition. Remember, again, this is a linear system, so if we add up a bunch of these inputs here, then the outputs just get added up. So the way to add up a lot of these is, of course, to do an integral. All right, so an integral, which is really a sum, is we're just going to integrate this thing here to add up a whole bunch of them. Notice the delta t here becomes delta tau becomes d tau here, which is our very tiny little time interval. So we have an integral on the left, and then of course we have to integrate everything here on the right to get this integral. Now, again, the reason we did all this is because this result here on the left is using the sampling property on the last slide. All of this stuff in the integral here is just x of t. This is the input signal. So for any input signal x of t, we have just derived or figured out what the output of our system is. The output of the system is going to be the integral of x of tau times the impulse response h of t minus tau, and this is going to be integrated over all tau. So that was sort of a whirlwind, quick derivation of convolution. The steps that we did there are not really as important as just being able to use the result and perform the continuous time convolution integral, which is what we're going to look at next. So the convolution integral is basically shown here in the yellow box. So the results on that previous page are extremely important and useful because it gives us the system's output, which is y of t, for any input signal x of t, just by knowing the impulse response h of t. So the convolution integral, in all of its gory details, is shown here. Notice here's the input, x of tau. This, we're integrating over this sort of dummy variable tau. This is x of tau multiplied by the impulse response h of t minus tau. Instead of writing out all of this kind of complicated integral here, we often use the shorthand notation. The output of a system is equal to the convolution of x, the input, and h, which is the impulse response. So y is equal to x convolution h, and remember again, this star symbol or asterisk is not a multiplication symbol, it means convolution in signals and systems. So here is our notation here. We have an LTI system with some input x. The output of this system is always equal to the input convolution with the impulse response. Again, this stresses the importance of the impulse response here. If we know the impulse response to a system, we can always figure out the output of the system for any input x of t, but we have to do convolution to get the answer. So what we're going to do in the remainder of this part of the video is go through several examples of convolution. Brace yourself, be prepared. This is not easy and it's not fun. So, grab a cup of coffee or whatever you need. This is one of the kind of necessary evils of signals and systems is we have to learn how to do convolution, although, as I'll talk about at the end of this video, we're going to find some shortcuts to get around this problem later in the course. But for now, we have to, live with this evil concept of convolution. So let's do some examples. This first example is pretty much identical to one of your homework problems. Problem 2. It's problem 22A in the homework. When you're doing the homework, you can use this explanation here to help you along. So the problem is to find the output of a system that has the input and impulse response given. So we're given that the input of the system, x of t, is an exponential function, e to the minus at times the step function ut. And this is shown in blue right here. Okay, so it's a decaying exponential function. We're told that the impulse response of the system is also an exponential decaying function, e to the minus bt times a step function. And so that's shown here in red, okay? And so our goal in this problem is to find what is the output of this system here that has, this particular impulse response h of t for this input here. What is y of t here? Well, of course, the output is equal to the convolution integral of x and h, where x and h are given here. But it's not as simple as just multiplying these together and integrating, because remember, this integral has a special interpretation because this impulse response here has been not only flipped or time reversed, but it's also shifted by an amount t here. So we have to do a little bit of work in order to get our answer, y of t. So let's get started here. So the first step is to rename these signals up here in forms that are going to be useful in the integral. So notice x of t has to be renamed to x of tau. Well, that's simple. We just take this function here, x of t, and wherever we see a t, we replace it with tau to give us this right here. Now, h of tau is a little more tricky. First of all, we can take h of t and just change it to tau, but notice that in the integral here, it's h of negative tau. So what we need to do is flip h of tau and do a time reversal. So remember, h of negative tau goes back like this. It goes to the left. All right, and so by replacing tau here and here with negative tau, we get e to the b tau multiplied by a step function u of minus tau, which goes to the left instead of the right. So that's shown in red. So these are the two signals here that we're going to need to integrate, but notice the h of minus tau is going to be shifted by an amount t. So we'll do that in the next step. Okay, so the next step is we're going to shift h of minus tau to the left by t, where t is initially some value less than 0. That means it's going to be pushed over here to the left, as is shown in this graph. And notice in this graph, there's no overlap between these two functions here. So the convolution integral, remember, is the product of these two. Well, since there's no overlap, the convolution integral is 0. So that's good. That tells us that our answer, or our output of our system, y of t, is just equal to 0 for all times less than 0. All right, now, you can go through and do all the, this is sort of the more formal mathematics of what we just said, but basically what we're saying is that, for t less than 0, this red function is shifted to the left, and there's no overlap, so the product of these two gives us 0. Okay, so let's go on to a more interesting part of this problem. Step number 4. We're going to shift h of t minus tau to the right by making t a positive number. So notice that when t is greater than 0, there is overlap between x of tau, which is the blue, and h of t minus tau, which is the red. And basically what we're doing here is when we multiply these two together, the only part that doesn't zero out is what's shaded here, because outside of the shaded region, one or the other of the functions is 0, so there's no overlap and there's no product. So in our integral here, in our convolution integral, notice that we only have to integrate from 0 to t. So notice I've changed the limits of integration from minus infinity to plus infinity to 0 to t. And notice also x of tau, this is from shown right up here. Here's our function. It's e to the minus a tau. And h of t minus tau is given right here. This is from actually one of the earlier steps. It's put in right here, e to the minus b times t minus tau. So now this is, we have to actually do some integration. So at first this looks like a, kind of a nasty mess, but it's really not that bad because these are exponential functions which are easy to deal with when they're multiplied together. So what I can do with this second exponential function here is break it up into its two pieces, e to the minus bt times e to the b tau. And what we can do here, notice we're integrating in tau, not in t. So our variable of integration is tau. That means e to the minus bt acts like a constant here because we're not integrating over t, we're integrating over tau. So we can take this e to the minus bt and bring it out in front of the integral. And what's left behind is e to the b tau times e to the minus a tau. And remember, for two exponential functions that are multiplied together, we just add the exponents. So we get b tau minus a tau, and you can see I factored out the tau, so I get e to the b minus a tau, and we're going to integrate over d tau from 0 to t. All right? So there are two cases that present themselves to us here. The first case is when a is equal to b. So what happens then is, notice if a and b are equal, then this exponent here goes to 0. So we basically have e to the 0, which is of course just 1. So we're integrating e to the minus bt of just d tau, and this is a trivial integral. The integral of d tau is of course just tau, and we have to evaluate it from t to 0, which gives us a factor of t in our answer. So our answer for the case where a is equal to b, it's equal to t times e to the minus bt. And again, this is valid for t greater than equal to 0. The second case up here is, what if b and a are not equal to each other? Well, then we have to just do, a little bit more of integration here. But fortunately, again, this is an exponential function in an integral, and you'll remember from calculus class, this is a fairly standard integral. Whatever the exponent is here, in front of the tau, the b minus a, that goes in the bottom out here, right? If you don't remember how to integrate an exponential function, look it up in your calculus book. So the b minus a goes under here in the denominator, and then what we're left with is, when you integrate an exponential function, you end up with the exponential function e to the b minus a tau, and when you evaluate it from 0 to t, we end up with this in parentheses. So you should, be sure that you can do these. This is just some basic calculus here of doing an integration. You end up with e to the b minus a t minus 1 in parentheses. So here's our answer for the case where a is not equal to b. All right, so we had in that last problem, it actually, believe it or not, that was a rather simple convolution integral because those exponential functions were pretty easy to deal with. I'm going to show you at least the outline of a problem that is a little more difficult because the functions aren't as easy to deal with. And again, I'm not going to go through all the nitty-gritty details here, but I just kind of want to point out, how this process of doing convolution can be very tedious and complex. So suppose in this case we have this input here, x of t, which looks simple enough. It's just a, kind of like a rectangular pulse of height 2, length 3. And let's say the impulse response looks like this. It is a linear function that starts at 4 and drops down here to 0 when t is equal to 2. So functionally, this h of t is negative 2t plus 4. The slope is negative 2. The y-intercept is 4, which you can see readily from this graph. So again, our goal is to find out what is the output of this thing. So we have to do the convolution integral. So we're going to do a lot of the same steps that we did in the last problem. We're going to take x of t and turn it into x of tau just by changing the variable. We're going to take h of t and turn it into h of negative tau by, flipping it, basically doing a time reversal. So instead of going to the right, it goes back to the left. And then we're going to start by shifting h of t minus tau over to the left and it doesn't matter how far, because if we shift it at all, notice they don't overlap at all, and so our output is 0 for t less than 0. This is kind of similar to the last problem we just did. Now here's where it gets fun. When we shift t positive a little bit, so it looks like this, well, now the overlap, there is overlap between x and h, and the tricky part of this problem, and again, I'm not going to go through all the details here, but it's finding a functional form of h of t minus tau. You can see it's a line, it's a segment of a line, so you can figure out, try to figure out the slope and all that. But in order to figure out the y-intercept as a function of t and so forth, I found the best way to do it was by using similar triangles. There's sort of like a big triangle here, and there's a smaller triangle, and they share the same angles, so they are similar triangles, so the ratio of their sides are equal. And so by using similar triangles, you can come up with this functional expression for this shifted impulse response, h of t minus tau. So it's equal to 2 tau plus 4 minus 2t. You can see it's a function of t here. So then, having this, we can actually plug this into the convolution integral and go ahead and do the integration and come up with this form, minus 2t squared plus 8t. This works as long as t is between 0 and 2, because once t becomes 2, we end up with a different situation, which we're going to deal with in step 6. So here's the case where t is between 2 and 3. What happens now is our h of t minus tau is completely shifted. Remember, we're starting over here and we're shifting it to the right. Now it's completely inside of this rectangular pulse up here. So that means the good news there is that it's much easier to figure out the overlap here when we multiply these together. Remember, an integral is just the area under the curve. So we just have the area under this curve here, which is the area of a triangle, 1/2 times base times height. And so that gives us our output, y of t is equal to 8 for the case where t is between 2 and 3. But of course we're not done yet, because we have to keep sliding this thing over to the right, and now it's going to partially overlap, which is shown here in step 7. So now if we keep shifting this to the right, so now this is for t greater than 5, for t between 3 and 5, we get partial overlap of h of t minus tau. So again, here we go. We got to figure out a functional form of this little piece of this function here. So again, using similar triangles and the geometry shown in here, there are a few steps, obviously, we can come up with this functional form for the output here, which is the area of that shaded region right there, and it's equal to 2t squared minus 20t plus 50. And then, finally, if we shift this whole thing over to the right by more than 5, then it's outside of, this 3 here, meaning there's no more overlap. So when we multiply these two functions together, we get 0, and thank goodness we're done, right? We've shifted it, all the way through, starting over here on the left, shifting all the way through, and we end up over here on the right, and now we're done because there is no more overlap. So the last thing we have to do is collect all our results for each of the cases for different values of t less than 0, t between 0 and 2, t between 2 and 3, t between 3 and 5, and finally t greater than 5. And here, here are all the results for each of those time intervals. Notice, we're just collecting everything from the last 8 steps. And plotting it, it ends up looking something like this. The output is 0, and then at t equals 0, the output comes up as a parabola. So this is an inverted parabola, which is shown by this function here. And then between 2 and 3 seconds, notice it's a constant value of 8 right here. And then between 3 and 5 seconds, it's falling, parabolically again, as a square of time. And then once we get to 5, it zeroes out again. So this is the output of that system for the given input. And obviously, this was quite a mess, right, to figure this out. But it's very doable, and this is how this system would respond to that given input. One of the properties of convolution, and we'll be seeing some others as well later, is that it is a commutative operation. And commutative just means that if you switch the order of the parts here that you're operating on, you get the same result. So for example, addition is commutative because 1 plus 2 is equal to 2 plus 1. Well, it turns out that convolution is also commutative, and it's not quite as obvious as addition, but if you take x convolution h, you get the same as h convolution x. I'm not going to go through the proof here, but just by doing, switching some variables around and so forth, in a few steps you can prove that, whatever you use, x or h, you can interchange those inside the integral and, interestingly, get the same result. So one of the useful things about the commutative property is you can actually simplify some problems. And again, I'm not going to go through this in any detail, but that last problem that we did that was very difficult, where we had h looking like this and x looking like this, if we do the convolution with h first and then x, so in other words we have h of tau times x of t minus tau, then what we're doing is we're shifting, we're flipping and shifting x instead of h. So here's h of tau. We're going to leave that here. We're now flipping, time reversing x. And this ends up being a much easier because x is just a simple rectangular pulse. It has a value of 2 everywhere except, once it becomes 0. So, now we can go ahead and start flipping and sliding x out here. There's no overlap, so we get 0. The next step, once we start to overlap up here, well, we've already got our function for h, which was given, and you can see the value of x is just equal to 2, so we don't have to use all those similar triangles and all that nonsense to try to figure out what the functional form here of these curves are. So we can just plug, this value of 2, just stick that right in the integral there, and we can do this integral, and we're going to get the same, end up getting the same result. And then we keep sliding x of t minus tau to the right. Again, you can just use this value of 2 here, which makes the problem much simpler. And the last couple of steps, we just keep sliding it along. We can do the integrals. Again, I won't go into the details here. And then finally, when we're all said and done and collect our results, we get the same final solution here. So, this problem, I think, was still difficult, but much simpler because we didn't have to go through the similar triangle or geometric analysis to find some of our functions. So we took advantage of the commutative property of convolution here and found a slightly easier way to do it. All right, so that was sort of a whirlwind introduction to convolution in these last couple of parts of the video. And some final thoughts here on convolution. One thing you immediately see is that convolution by hand, which is what we're doing right now in this course, is not easy or fun. And you're going to get some more practice with this in the homework, and you'll get to see firsthand how difficult it actually is. So the message here is that even the simplest convolution problems are usually difficult and or tedious, as we saw in the examples here. In fact, it's kind of interesting that the word convoluted, you've heard that used elsewhere, it means complex and difficult to follow. So, like a convoluted plot of a movie, something like that, right? Well, so I guess it's a fitting name that we call this this method in signals and systems convolution, because it is complicated and it's difficult to follow. Computers obviously are much better off at doing this kind of thing because it's a lot of just calculation and brute force computation and things like that. But here's really the good news for us, is that we can avoid convolution completely by working in the frequency domain using Fourier methods. And this is going to be, one of the key things that we're going to do later in this course, starting in chapter 3 and especially in chapters 4 and 5. We're going to get into these frequency domain methods using Fourier series and Fourier transforms. So that will be the subject in the future. So keep that in mind when you're doing these grueling convolution problems. You won't have to be doing these the whole course. This is just sort of a necessary evil right now to do by hand, and we will, there's light at the end of the tunnel because we're going to figure out a way to do this much more conveniently without having to do convolution later in the course. So that is it for now. I will see you soon for part 3 of this chapter's lecture later. Goodbye.